right? I thought there'd be data. Is anyone out there?
Welcome back to Mathematical Statistics. We kind of have a fun day of new stuff today. I brought cards, but I'm not really going to do anything with them. But I do need to talk about, let's see, conditional probability. Okay, so if you've had, depending on your background, I think some of you are probably well-versed in conditional probability, but some of you less so. So please bear with me for a little bit, but conditional probability means that I give you some kind of information and then you have to compute a probability. So if I ask you the probability that I just randomly selected this card and I asked you what the probability of it being a king was, you would say 4 out of 52 because there are 4 kings in a deck of 52 cards. But if I look at it and I tell you that it's a face card, that means it has a face on it. So it's a jack or a queen or a king. And now I ask you the probability it's a king, then you would say, well, now I'm down to 4 out of 12. So it's 4/12 or 1/3. And that's conditional probability. You're given some information. And we're going to start using conditional probability in MathStat today. And so let's do it. And we are starting the machinery for the UMVU. The notation for, oh, it was a 7 of diamonds. We all lose. Okay, I don't know what that was about, but conditional probability, a little bit of a review, and maybe even some new things in here for those of you that have had it. These are going to help us define a special class of statistics on which the UMVU is based. Okay, so first, and just really briefly in terms of events, so if we have events A and B, like think back to whatever probability class you may have taken at whatever point in your life, like A is the event I drew a king, and B is the event I drew a face card, then the conditional probability of, or that A occurs, given that B occurs, is written with this line. So this is given. And so again, A could be drew a king, and B drew a so-called face card. And when you want to compute something like this, you kind of are shrinking your universe. I mean, you knew exactly what to do. Once I told you you drew a face card, you then stopped thinking about all 52 cards. You just thought about the 12 face cards. And that's what conditional probability is, especially when you think of probability in terms of Venn diagrams. So there's some probability that an event A occurs, which could be thought of as the area of this set A that I drew. And if I have another event B, and I want the conditional probability that A occurs given that B occurs, I know the outcome. Think of the outcome as like darts going onto this board. Actually don't, because that would involve a uniform distribution. But if an event lands in B, what is the probability? It's also in A. So this is just going to be the probability of A intersect B over probability of B. In other words, you're reducing the space to B, and then within that, you're looking for A to happen. We're going to turn this into PDF stuff, and we're going to be talking about joint PDFs for X1 through Xn, conditioned on certain statistics, like what is the joint PDF for X1 through Xn, given that you already know the sum. Let's do it. So if we have random variables, X and Y, so let's suppose that they are discrete, just to start. Then, we write the probability that X equals X and Y equals Y with a comma, right? That usually means and. I mean, it always means and. And we can talk about the conditional probability that X equals X given Y equals Y. So we would write it as the probability X equals little x given, that's that horizontal line, Y equals Y. And it would be defined totally analogously to this up here. It's going to be the joint probability that X equals X and Y equals Y divided by the marginal probability that y equals y. Okay, and we have notation for both things on this side. On the top, we have a joint PDF, which we may or may not subscript, but I'm going to subscript. This would be an fxy of x and y divided by a marginal PDF for y. So that's all known notation to us. And whether, depending on your background, you may or may not have seen this kind of notation. So this may be new. A PDF for x given y, and then the arguments x given a little y. So there's our first conditional PDF. And then in the continuous case, we can't talk probability, but it's completely analogous. So I'm just going to write this circle again, but not write the probabilities. And yeah, and this is a perfect opportunity for cut and paste. So the conditional PDF for x given y is just defined as the joint PDF over the marginal PDF, even though you can't really think of these as probabilities. And in the continuous case, we know that the probability that x equals some x is always 0, or that y equals some fixed y is always 0. But it does make sense to talk about something like the probability that x is, say, less than or equal to x, given y equals y, because that has been observed and it's over, right? So I gave an example at the beginning of class for a continuous random variable. What's the probability that the next person you see today is exactly 64.17337246 inches tall? And that's vanishingly small, especially as you get more accurate. But assuming you can measure with total accuracy, once you observe them, you have the person's height. And so it does make sense to have equals after the conditional line. And so if you wanted to compute this probability, this is a CDF. It's actually a conditional CDF here, but I don't care about that. We're not going to be using conditional CDFs, but you would integrate from minus infinity to x, the PDF for x, and then conditioned on y being y. And you would run over all the x's. And just one more quick example before we get on to the real things from today. We can talk about conditional expectation. So the expected value of x given that y equals y. And this is just going to be the integral of x against the PDF for x given that y equals y. And it's an average over the x's, so you would sum or integrate in this case over all the x's. Or it may be a sum if these guys are discrete. Okay, great. There's a few properties we're going to need to know about conditional expectations and conditional variances before I can define this special class of statistics today. So, I think got everything there. Yeah. So here are some properties of expectation. Oh, actually, before this, I'm not going to go through all of the properties of expectation, but this is just an expectation against a PDF. So I wouldn't really use this notation because it kind of means something else often in statistics. But you could think of this as the expected value of x, and then just have like a little subscript to say, oh, y has been given, and then you can really see the linear operator properties. Like we have everything we could possibly want because it acts like any other expectation. It's just that the PDF is a different PDF. So any nice properties of expectation that we have, like the law of the unconscious statistician and linear operator stuff, will still hold in conditional land. Okay, so that said, these aren't really properties. It's just, it's me writing another list of things. Sometimes I write lists of stuff, and I probably should have done that. I'm actually going to throw a variance property in here too. And actually, it's going to be mostly about conditional expectation and variance. So the title was just wrong on so many levels. But the first thing in my list of things is just to point out something you already know, and that is the expected value of a random variable is a constant. A constant meaning non-random, and I always say that because we've been talking about sequences of random variables, and you might have the expected value of an x sub n be an n minus 1 over n theta, and that maybe doesn't look constant to you. It's not constant in time, but it's not random. So that's always what I mean by default when I say constant. Okay, so the next thing is the new expectation we just learned about, the expected value of x given that y equals y. This is a function of y. I mean, just look at how we defined it. We're going to integrate over x, and we're going to plug stuff in for all the x's, but the y is going to be floating around there. So it's some kind of function of y. And I'm going to say g of y. Things we're going to be using today are expectations like this. The conditional expectation for x given capital Y. And this is defined to be this function of y, but with the capital Y plugged in. So this is a random variable. So this is the g from property 2 with a capital, trying to make that really capital Y plugged in. And so this is a random variable. And so it has a distribution, it has a mean, it has a variance, it has all sorts of things. And whenever I need to compute an expectation like this, I always just first rewrite it like this and work it out. It just, I don't know why. I think it makes everything seem a little more concrete. And then at the end, I get the function and I plug in the random variable. Okay, so the next thing is truly a property. Like those weren't really properties. And that is that you could write the expected value of a random variable x as the expected value of the conditional expected value of x given y. A very Markov thing to do if you've come out of Markov. We do a lot of conditional stuff there. But remember, this expectation in the inside here is a function of the capital Y, which is random. And so then we get to take its expectation with respect to the PDF for Y because it's a function of Y. So let's prove this, and let's prove it that way by starting with the right-hand side. The expected value of x given y. So again, this thing inside is a function of capital Y. So to compute this outer expectation, I would integrate from minus infinity to infinity the function with a little y plugged in. And then I would integrate it against the PDF for little y. And then we already defined how to compute the inner expectation. It's another integral. So this would be the integral minus infinity to infinity of the integral minus infinity to infinity of x times the conditional PDF for x given y dx. And then out here I've got fy, y, dy. So if I pull everything together, namely pull this constant inside the x integral, then I've got the conditional PDF for x given y times the marginal for y, and that gets you back to the joint PDF for x and y. So this is an integral x times the joint PDF. And those integrals are still going minus infinity to infinity, but I don't feel like writing them. And if we switch the order of integration, this is something I'm doing right now in measure theory, doing the technical stuff. Here, I just want you to assume you can do it. As I've said before, probability stuff is always nice because everything's nice and bounded. And so if you switch the order, then you'll have the integral of x, integral f x y, x and y, dy, dx. And then this inner integral will give you the marginal PDF for x. So then you have x times the marginal for x, and that is the expected value of x, and that's what we wanted to see. Again, this thing inside, this expectation is a random variable. It's a function of y, so it does make sense to take an expectation of that random variable. Excuse me. All right, so the last thing before we can talk about this new class of statistics is a formula for conditional variance. And unfortunately, it's a little more complicated than you might think, if you're doing your statistics unconsciously. Um, you might want to write this and put variances in for the e's, but it doesn't work that way. So let me tell you how it does work and prove it. So this would be property 5. If I want to compute the variance of a random variable x, and I want to drag another random variable in because it makes the computation easier, um, then I could write this as the variance of the expected value of x given y, but that's not all, plus the expected value of the variance of x given y. That's not so nice. No one would do that unconsciously. Okay, so let's prove it. I can start with, I'm going to start with the last term over here and then try to get this guy minus this guy. So the expected value of the variance of x given y. The variance is defined as it always was in terms of an expectation, or maybe the other more computationally pleasing formula where we say the variance of x is the expected value of x squared minus the expected value of x all squared. It's just that the given y comes along for the ride. So this is the expected value of x squared given y minus the expected value of x given y all squared. Because really, this is just a plain old variance, but the PDF you're integrating against is a conditional PDF. So I am going to run this. Well, actually, before I do that, I do know this thing inside the square here is the expected value of, no, I don't know that. I'm going to run the expectation outside through. So I get the expected value of x squared given y minus the expected value of this whole expectation squared. And the first expectation, it's that iterative conditional expectation. This is just going to be the expected value of x squared. We just proved that we didn't have a square here, but actually the proof that we did above would hold like for any g of x right here. So you'd get an integral of an integral, and then you'd swap some stuff. So I probably should have proven it for a general like g of x in there. But this is what we just did in the previous. This is from number 4, which was a little more specific. Okay, so over here, I can compute the expected value of something squared. Remember our usual trick. The expected value of like an x squared is the variance of x plus the expected value of x all squared. What's going on with my voice today? And I'm going to do that here. It's just that instead of the x, I have this entire conditional expectation. And I erased. So this is minus the variance of the expected value of x given y plus the expected value of x given y all squared, just using this guy. And the final expectation inside the square, this is just going to be the expected value of x. And that gets squared. So the first term and the last term are the expected value of x squared minus the expected value of x all squared. There's the variance we were looking for. And then minus this variance of the expected value, blah, 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 blah. And we are done. Because if you look at the line that is at the very top right now, that's what we wanted to see. All right, how are we going to use this? Here is this exciting new class of statistics that is both really special because all UMVUs are based on these statistics, and yet really not special because almost all statistics falls into this class of statistics. And that is the idea of sufficient statistics. So I'm going to define this and we're going to figure out how to find some, but all UMVUs are based on sufficient statistics. But a whole lot of statistics are sufficient, so that doesn't really help us. It's just a very beginning of narrowing some stuff down. So recall that a statistic is any function of the data. And so I have a random number generator in the hallway, and I am generating Bernoullis for you. And you want to estimate the P for a Bernoulli. And I I'm going to go out in the hallway to that random number generator and I'm going to bring you back some data so you can estimate P. And I could walk in with my arms full of spilling X's, or wouldn't it be enough? Wouldn't it be sufficient if I just brought you the sum? Come on now. What else are you going to do with the rest of the data? I think it is sufficient if I bring you the sum when you want to estimate P. Do you really need the max or the individual values? Depends on what you're trying to do, I guess, but that's basically what a sufficient statistic is. I mean, there's a formal definition, but it is all you really need to estimate the parameter of interest, meaning that once you have it, bringing in all the original X's is not going to give you any more information. So let's write that down. Okay, so first, an informal definition, and then the formal definition, which will involve conditional PDFs. So a statistic, this is any function of the data, and I have been using throughout a capital T to denote like a generic statistic, but this being sufficient, I'm going to call it S, like an S, some sort of like, I don't know, that's supposed to be a lowercase cursive S, so that my lowercase non-cursive S could be this with the actual data plugged in. But anyway, I'm going to call the statistic S, and it is sufficient for theta. I guess I should have started with a setup. So I've got x1 through xn, maybe IID, maybe not, but they have a joint PDF, f of x and theta. And people say sufficient for theta, but I think it would make more sense to say sufficient for estimating theta. If it condenses the information in the random sample down to a statistic, one-dimensional or maybe two-dimensional or maybe three statistics, without sacrificing any information about theta. So if it condenses the info in the random sample, I guess if I say random sample, I am talking about IID things. But this definition does not necessarily need IID things. So it's sufficient for estimating theta if it condenses the info in the random sample without sacrificing any information about theta. And then the formal definition will tell you exactly what this means. So again, it doesn't really need to be a random sample because you just might have a joint PDF and not built up from IID things, and random sample means IID. So here's the formal definition. I'm just going to keep random samples. I think it's going to be a little easier. So we'll talk about non-random samples after we've gotten a little bit further. So I'm going to let x1 through xn be a random sample from a distribution with PDF f of x and theta. So we say that a statistic S, that's supposed to be capital, S is a sufficient statistic, people say for theta, they also say for the model. Um, so they never say for estimating theta. People say sufficient for theta. And what they mean is sufficient for the model. And what I mean by that is if I brought you Bernoulli random variables and asked you, isn't it enough that I bring you the sum? You could say the sum is sufficient for estimating P, or you can say that the sum is sufficient for the Bernoulli distribution in the sense of this definition that I need to finish. So sufficient if the conditional, so this is why I started with all this conditional stuff, the conditional distribution of the data, the x1 through xn, given S does not depend on theta. So let's check our Bernoulli example using this definition. Okay, so the example we've already kind of talked about is x1 through xn IID Bernoulli, oops, with parameter p, and we're guessing, but I'm going to tell you how to find sufficient statistics. We're guessing that the statistic S, that is the sum as I goes from 1 to n of the xi, we're guessing that this is sufficient for, for the p, or the Bernoulli, or for estimating p. Just using the informal idea of, isn't it just enough that you use this one statistic and you don't need all of the data? So let's prove it and hopefully illuminate this definition that I just wrote of sufficient statistics. So I want to look at the joint distribution of all of the x's given S, and hopefully once we work that out, it is parameter free. There's no p at the end of the calculation. So I'm going to look at the joint PDF, which in this case is probabilities. So the probability that x1 equals x1 out through xn equals xn given S equals some little s. We're going to do kind of massive computation. And in the end, we're going to have maybe a huge mess, but hopefully no letter P. That's enough to say that this statistic is sufficient. So given you have this isn't helping you get at P. Okay, so let's do it. We learned today how to do conditional probabilities. This is just kind of a high dimensional version. And 40. This is let me write it up here. This is a big fat joint probability. x1 equals x1 out through xn equals xn and s equals s over the probability that s equals s. That's just how you define that conditional probability. Okay, and I just want to do a little side calculation or example to show you what to do with this numerator. So suppose I just had two random variables, x and y, and we were looking at the probability that x equals, and they don't even have to be Bernoulli, so like x equals 2, y equals 3, and x plus y equals 5. So in this example, the x plus y equals 5 is redundant information, and this is the same thing as the probability that x equals 2 and y equals 3. If I left myself some marginal space, I would circle this and write, I'm doing it, look, redundant. Okay, and one more example here. If you have the probability that x equals 2, y equals 3, and x plus y equals 11, that's just 0. That can't happen. So that's what I'm going to do a little more generally with the conditional probability we just wrote down. This is going to be 0 if, oh, yeah, all right, I wanted some more notation, but it's going to be 0 if the little s is not equal, so I'm trying to really emphasize that that's a small s, is not equal to the sum as I goes from 1 to n of the little x's. I'm doing exactly this for this larger scale thing. Okay, and this does not depend on p, so that's okay. again. I'm going to sneeze. And of course I'm not once I mute it. So this does not depend on P. So far we're okay. So now I want to do that conditional probability in the case that little s does equal that sum. So in the case that little s does equal that sum, then the probability that, I don't think I should rewrite this whole thing, but I'm doing it as if I had no control over the situation. This is the big fat joint probability over the marginal probability for S, and I can drop this part, just like I dropped, just like I did over in the example on the side, because it is redundant. Okay, so now I can compute this probability pretty easily. On the top, I've got IID things, right? It's a probability, it's just a joint PDF on the top. On the bottom, I've got a random variable whose distribution I know because the sum of binomials is Bernoulli. The other way around. The sum of Bernoulli's is binomial. Sum of Bernoulli's. So on top, I get little p to the x1. I'm just going to write this once, and then 1 minus p, 1 minus x1, and I have an indicator. And kind of important here, you know, sometimes I use indicators and sometimes I don't, but I always use them when I'm trying to state a result that involves this is parameter free. Because if the parameter was in the indicator and that somehow got left behind, then that's bad. So the joint PDF on the top is the product as I goes from 1 to n. You know what, let me just go for it. I'm going to multiply them out. This is p to the sum of the x's, 1 minus p, to the n minus the sum of the x's, and then a product of indicators. As I goes from 1 to n, the indicator that xi is in the discrete set 0 to 1. Divided by, so the binomial PDF for the probability s equals little s is n choose little s, p to the s, 1 minus p to the n minus s, and then an indicator that says that s has to be in the set 0, 1, 2, up to n. Okay, well, because we're in the case that little s is equal to the sum of the little x's, then I can cancel lots of stuff because this p to the s is precisely this p to the sum of the x's because we're in that case. Same thing here. Since this little s is equal to this sum, those are going to cancel. And the rest, who cares? You don't have to simplify it. There's no p's left. That's the point. So we have, so we've proven that the statistic, the sum of the x's, is sufficient for the parameter p or for the Bernoulli distribution with parameter p. And probably I should do this, which I'm not really going to do. Like the final recap would be this guy given this guy is equal to 0 in one case, and it's equal to this other thing in another case, and then you say there is no parameter p. So yes, S is sufficient. I like to just say for the model. You don't want to be doing this, especially, you know, for more generic distributions. You probably are not going to know. I don't know if you would know the distribution of the statistic and be able to do that. Now, if things are continuous, you do it exactly the same way. You can't write probabilities because that doesn't make sense, but you would write the joint PDF conditioned on S equals S. So I don't know if we need to, I don't know, do we need to do that? In the continuous case, you would just start with the big fat conditional joint PDF, and you would write it as the bigger, fatter joint PDF over the marginal. So it's the same thing, but you just can't interpret these things as probability. Okay, but that S equals S thing is always gonna happen in the numerator. We're always gonna get either something redundant or something with probability 0. So let me go back to probabilities. If you've got like the probability that x1 equals some x1 out through xn is some xn, and then you've got S. So a statistic S is some function of the x's. If you've got S equals some little s, this is always going to be 0 if little s is not equal to the function of the little x's. And it's always going to be just the probability for the x's. How horrible is that? I'm trying to show it ends with the x's. If little s is equal. So really showing that a statistic is sufficient, especially when you have a random sample, it boils down to this. All comes down to this. We're gonna start with a conditional density. We're gonna write it as a fraction. We're gonna get 0 or cancel something out of the numerator. And so the top is gonna be a joint PDF. And if we have a random sample IID, we're gonna come down to a product on the top over a marginal PDF for a statistic S on the bottom. And we want this to be parameter free. So it could be a function of the x's, and let me call it a function of the x's, like some kind of h of x1 through xn. But the notation is suggesting no parameter. And this leads us to Neyman's factorization criterion for sufficiency, which I just have enough time to get down, and we'll talk about it next time. He's not always attributed. It's not always attributed to him. It is, but not in the title. So it's called the factorization criterion for sufficiency. This is awesome because this will give you a sufficient statistic and prove it all at once, so you don't have to guess at one. So it says the following. It says that x1 through xn are IID from a distribution with some PDF f that depends on theta. And it says that a statistic S, which is some function of the x's, is sufficient for this model or this parameter or theta if and only if the joint PDF factors into a function of the x's only, which I'm going to call just like I did above, h of x, and another function that depends on the x's only through the sufficient statistic. Let me say that differently. X only, and then x n parameter, but we're going to look into that function and see how the x's are represented. They're going to appear in like a clump. So if we do this with the Bernoulli distribution, we're going to see a function of the sum of the x's and the parameter. And so the last thing I want to say is this is useless because you know what else is sufficient that I bring you from the hallway? All of the data. Since a sufficient statistic can be vector valued, the statistic x1 through xn is always sufficient, right? So it is sufficient that I bring you one more quick example, uniform 0 theta. It's sufficient that I bring you the maximum, I would think, but I can also bring you the maximum and minimum. Who cares? That's still sufficient. There's an idea of minimal sufficiency, but almost everything is sufficient because it's always sufficient for me to bring you all the data. So okay, so I'm out of time. Sufficient statistics will be at the core of finding an MVU, and yet not so helpful because a lot of things are sufficient. We're going to do more examples next time, and we're going to use this factorization criterion and see how it works. And also factor our joint PDF in several different ways, resulting in several different sufficient statistics. So we need another property for our statistics. and that is the concept of completeness. Next time on mathematical statistics.